Welcome to science class. Today we are going to learn about radiometric dating. What I want to focus mainly on today is not so much the physics and chemistry behind radioactivity and radiometric dating, but rather how it is used as a tool to understand Earth's past. That's what this unit and this course is about, understanding Earth. Plus, it's been 8 years since I took a physics course and 9 years since I took a chemistry course. Radiometric dating has been invaluable to science. In these first 2 videos of this unit, I have argued against competing claims about Earth's past by using evidence from stratigraphy and the fossil record. But radiometric dating isn't just evidence, it's proof. Radioactive isotopes are like incredibly long-lived clocks. By studying them, we can see how they have changed at the nuclear level over thousands, millions, or billions of years, which allows us to know that the Earth formed 4.56 billion years ago. Let's get started. Historical geology before radiometric dating was all about relative dating, putting events in sequence, as opposed to absolute dating, which is determining the actual age of a sample. We can look at the layers of rock and fossils and determine which layers and which organisms appeared first on our planet, but not actually when they appeared. We can speculate, but scientists don't often pretend to know something they don't. Was the world created 6,000 years ago, and did dinosaur and man walk through the Garden of Eden? Of course not, but did that mean Earth was 2 million years old, 2 billion years old, or what? We didn't know. One of the first published attempts at truly calculating the age of the Earth was done in 1862 by the Scot-Irish mathematician William Thomson, better known as Lord Kelvin. Thomson based his calculation around the amount of time it would have taken Earth, which he assumed was molten during its formation, to form a solid crust. The conclusion? Earth was between 20 and 400 million years old. That's a pretty wide margin of error, not to mention it isn't very close to the real date. Thomson knew nothing about radiometric decay, which actually does a significant amount of work in keeping Earth's interior incredibly hot. So his slow and steady cooling model wasn't an accurate reflection of what really happens. Other scientists in the same century tried to date the sun, but they had no idea about nuclear fusion, which keeps the sun burning for much longer than an object would if it merely radiated its heat away, like a burning log does. Finally, some attempts at measuring the depth of sediment in the oceans, or the amount of salt in the oceans, were used to try and calculate the age of Earth. None of these estimates put Earth at more than 100 million years old, 45 times younger than it really is. Now, radiometric dating was only possible once we learned that atoms really do exist, and that they are made of subatomic particles, protons, neutrons, and electrons, and that some elements are radioactive. We won't cover the history of that, but here are the names you should know if you'd like to learn their contributions. So what does it mean if something is radioactive? Radioactive is a chemical property that some isotopes of some elements have. Elements that are radioactive transform into different elements over time. And that's elements, not compounds. They're not forming new bonds. The actual nuclear structure of the individual atoms is altered. An element is defined by how many protons there are in its nucleus. Many elements have a nucleus with, of course, the same number of protons, but different amounts of neutrons. That's what an isotope is. Uranium has 3 different isotopes: uranium-238, 235, and 234. That number is the atomic mass. A uranium atom always contains 92 protons, so do the math, and uranium-238 has 146 neutrons. Uranium-238 atoms transform, through radioactive decay, into lead-206. Lead's atomic number is 82, so 10 protons have been lost from each uranium atom as they transform into lead. How does that happen? In a few ways. An electron can be absorbed by a proton, Electrons are negatively charged, so this ends up neutralizing the proton. It becomes a neutron. When this happens, the element moves backwards one spot on the periodic table. The opposite of this also happens. A neutron can release an electron, transforming it into a proton, which transforms the element into the element ahead of it in the periodic table. These are both called beta decay. Alpha decay is when two protons and two neutrons spontaneously are broken away from the atom's nucleus. This alpha particle actually becomes the nucleus of a helium atom. This transforms the element into the element behind it 2 places on the periodic table. Many radioactive isotopes will actually decay in all 3 of these ways as they transform into stable isotopes. Uranium-238 doesn't just skip down straight to lead-206. It jumps forward and backwards on its way to becoming lead, existing as different elements in the process. That's pretty weird. But we can measure how long it takes for the original isotope, which we're going to call parent material, to decay into stable isotopes, which we're going to call daughter products. Specifically, we can measure the half-life, which is the amount of time it takes half of the nuclei in a sample to convert to stable daughter products. The half-life of uranium-238 is 4.5 billion years. So if you have a sample of rock and you find exactly 10 grams of uranium-238 and 10 grams of lead-206, it's 4.5 billion years old. All radiometric isotopes have a unique half-life, which ranges from seconds, minutes, hours, to billions or trillions of years. Radioactive decay is actually downright spooky. Let's imagine we have 64 grams of a radioactive isotope, and this isotope has a half-life of 5 million years. 5 million years from now, then, 32 grams of this sample will become the new daughter product. What happens 5 million years later? The remaining 32 grams of the original parent material should all decay, but they don't. Half of them do. Then in 5 million more years, half of those remaining atoms decay, and so on. No matter how much parent material you have, it always takes the exact amount of time for half of it to convert to stable isotopes. This means that the last atom of the original parent material sticks around for maybe thousands of generations of these transformations, then just spontaneously goes, meh, alright, I'll change now. Now, it's very difficult to measure individual isotopes in a sample of rock. The technique is called mass spectrometry. Claire Peterson was the first person to successfully analyze the age of Earth, which he did by dating meteorites, which Earth was made from. That happened in 1955, and the results were published in 1956. But he started the project in 1948. Part of why the results took so long to find was that they were trying to measure lead isotopes, but the samples had thousands of times more lead than should be possible. This was because all gasoline contained lead, and cars were aerosolizing it all over Earth. Peterson was finding lead contamination in Greenland and Antarctica, thousands of miles from civilization, and in the oceans. Lead is a potent neurotoxin, and Peterson fought for decades to have lead gasoline phased out. So meteorites are always dated to around 4.5 to 4.7 billion years old. When we date rocks on Earth, we get a range from a few thousand years old to around 4.1 billion years old. Why is that? When you date a rock on Earth, you are determining when the rock crystallized from magma on Earth's surface or close enough to the surface so as to begin crystallizing. Earth is dynamic, and because of tectonic activity, new material comes up to the surface constantly, and old material is plunged back into the mantle or buried by kilometers of solid Earth constantly. This is how we know seafloor spreading occurs, for example. The ocean crust has been dated to progressively younger dates as you get closer to the mid-ocean ridge, where magma comes to the surface. Meteorites in space obviously aren't undergoing any real changes, so they are incredibly reliable and stable models for dating the planet. So on Earth, we can usually only date igneous rocks directly. You can date bones and tissues using a method called radiocarbon dating, but the sample must be less than 75,000 years old, And as we discussed last time, fossils aren't bones, they're rocks. Then how do we tell how old fossils are? Well, we have to date surrounding rock layers, then determine if the fossils were deposited before or after those layers. So we use a combination of relative dating and absolute dating. Now, one fossil site can't tell you exactly when that fossil formed, or when that creature evolved or went extinct. But thousands or millions of individual samples can. This is why scientists publish their results. We have found enough fossils to be able to narrow down when these major evolutionary and also extinction events occurred. Dinosaurs show up 233 million years ago, and went extinct 66 million years ago. If we find some older dinosaur fossil that is 250 million years old, we would modify our model. But it's highly unlikely that that would happen. At this point, we have quite a lot of what we've found narrowed down to respectfully tight margins. But there will always be some gaps. Now that we know how old Earth is, and can date individual fossils and formations on our planet, we can begin to construct a timeline. Next time, we will do exactly that, and peer into the 4.5 billion year long geologic timeline of Earth, and see what kind of events happened and when. Thanks for watching.